see that. It is not urgent that you know this derivation, but it can be helpful for people. Bernoulli's equation has to do with fluids that are moving through containers that change their shape, and it also incorporates pieces of the pressure change due to the change in depth. So it kind of includes the first thing we looked at today, but also incorporates changes in speed due to changes in velocity. And it relates together three things. It relates together the pressure that the fluid exerts on the container. It relates the kinetic energy per unit volume that a fluid has because it's in motion. And it relates the potential energy per unit volume that a fluid has because of how high it is away from the ground. So what we're going to be doing is we're going to be thinking about a pipe here that rises and also changes its cross-sectional area. And that's going to be the system where we're going to derive Bernoulli's equation. And what I want you to imagine is that we have this dark blue chunk of water, say, here, that's moving through a pipe, and it ends up moving over some amount of time to be at this location on the other side. The pipe is widening as you travel along it, and so you can see that here the length of this dark blue section is decreasing as it moves across because the cross-sectional area is going up, and the volume has to stay the same because it's incompressible. Because we're looking with an ideal fluid, there's no frictional losses here. And so we're going to use conservation of energy. And the way we want to use conservation of energy is that the net work done on moving something from one side to the other will be equal to its change in kinetic energy and change in potential energy. And in this case, that potential energy is just the potential energy due to gravity. The hardest thing to look at is what is the total work or the net work done. And what we're going to imagine is that this chunk of fluid has to be pushed inward at a constant velocity because of the pressure of the fluid behind it. So there's a force that's being exerted by the fluid that's on this part of the pipe that's not shown. And the work that's being done will be equal to that force times the displacement. And it will be, the force comes from the pressure times the cross-sectional area. So we have this P1 times the cross-sectional area 1. And then to move that displacement, delta x1 or S1, it's going to, that distance that it goes is going to be the velocity times the time. And interestingly, what we end up with is that when you have that area times the velocity times the time, we can think about that velocity times time gives you a distance, that delta x. That delta x times the cross-sectional area of this cylinder gives you a volume. So we can write the work done as the pressure at this point in the fluid times the volume of this dark blue chunk. Okay? So just to look at that one more time, we have the work being done by the fluid that's not shown here, pushing this chunk of fluid to the right. The work is the force times the displacement. The force is the pressure times the cross-sectional area, and the displacement is the velocity times the time. And so by looking at the velocity times the time as the displacement, area times displacement is the change in volume. So the work done is the pressure times the change in volume. And you can do the same thing with the work that this fluid does when it goes out of the pipe. So on the way out, it does the opposite. The work is being done by this fluid on the fluid that's shown over here, or that's not shown over here. The calculation is going to be exactly the same. The difference is going to be that this is work done onto the fluid that's coming in, and this is work being done by the fluid that's going out. Of course, the values might be a little bit different because this velocity is possibly lower because the cross-sectional area is larger. This displacement is going to be a little bit different, and that pressure is going to be different. But the volume is going to be the same. So this pressure 1 times volume 1, pressure 2, and the same volume. Oops. Did I have another piece there? Nope, that was it. So work is done to the fluid at the input, work is done by the fluid at the output. So I wish I had made this reveal, but I didn't. So the total work done is the change in kinetic energy and change in potential energy. So we just calculated the net, or we can calculate the net work. We know it's the work done to the fluid, pressure 1 times that volume, the work done by the fluid, pressure 2 times the volume. And so the net, pressure 1 times the volume minus pressure 2 times the volume, just P1 minus P2 times the change in volume. The other pieces are also pretty easy. The change in kinetic energy. This is going from moving at velocity v1 to moving at velocity v2. And so the change in kinetic energy will be 1/2 mv squared, which is 1/2 times the density times the volume times v2 minus v1. Final velocity, initial velocity. So we have 1/2 rho volume v2 squared minus 1/2 rho volume v1 squared. So that's our change in kinetic energy. And then the change in potential energy associated with gravity just is this mass being moved up by a height h. The mass is density times volume, g, and then h is z2 minus z1, whatever the difference in height is. Now, the cool thing is here, in this energy expression, because we're working with a fluid, we prefer not to have a specific volume, but we think about any volume. So we have a volume in the first term, the net work being done. We have a volume in the second term, the change in kinetic energy, and a volume in the third term, the potential energy due to gravity. So we're going to cancel that out everywhere. Now we just have a difference in pressure is equal to a difference in kinetic energy plus a difference in potential energy. And generally, this gets rearranged to show all of the things on the left-hand side, P1, V1 squared, Z1 on the left-hand side. So we have pressure 1, the sign changes here, plus 1/2 rho V1 squared, the sign changes again, plus rho G Z1 is equal to, move this over to the other side, and it becomes P2, becomes 1/2 rho V2 squared plus rho G Z2 is a constant. So pressure, kinetic energy density, potential energy density, the sum of those three terms must be constant as long as you have an ideal fluid moving through your system. And as a reminder, the rules for an ideal fluid are that it is incompressible, meaning a change in pressure doesn't change the volume, so these volumes are all the same. And there's no friction, so we don't have any energy lost, so we can use conservation of energy. And as long as you have those two things, you're fine. So that's the derivation of Bernoulli's equation. Very briefly, let me just tack onto this, looking at a common example, which would be looking at how if you poke a hole in a container at different depths, that the velocity of the water leaving that container will be different at different depths. So let's take a look at that. So we have water tanks that are at the top of an apartment building that allow for high velocity water in the showers on the lower floors. And so we're going to have this 20-story building. We'll make them 3.5 meter tall floors. So 20 stories up, where it's say 70 meters. And the top of this water tank is going to be at atmospheric pressure. And then it's going to say, assuming that that's at atmospheric pressure, what would be the output faucet speed on the 18th floor? So we can think of this like hole in the side of the bottle. as like a shower head that's on the 18th floor. And then maybe this is a shower head on the 10th floor, and this is like a shower head on the second floor or the first floor, right? So what we're going to do is we would say that the sum of the pressure plus the velocity, or the kinetic energy term, plus the potential energy term would have to be the same here at the top of the tank and here where it's coming out of the faucet. We know what the change in height is. So at the top of the 20-story building, it's maybe at 70 meters. On the 18th floor, maybe it's 7 meters or so down from there. So you have it at 63 meters. So you can do something with the rho g h term. And then we can look at the kinetic energy term. At the top of this tank, because the area is so large, and compared to the faucet where the water is coming out, the continuity equation tells us that this velocity is approximately 0. So we'll throw away the kinetic energy term on the input. And then we look at the difference in pressure. On the input side, the pressure is the same as the pressure of the atmosphere. And on the output side, the pressure is the same as the atmosphere. So there's actually no difference in pressure at these two locations. There is down here inside of the faucet, but once you open it up, the pressure will be the same, and that's why it flows. So we really just end up with a change in potential energy density leading to a change in kinetic energy density. And so it really ends up being the same thing as if you just dropped the water 7.5 meters. So it's going to be pretty quick. We can do that calculation. In fact, if you go to very tall buildings, you may need pressure reduction because it could be that the water would be traveling so fast out of the faucet that it could be dangerous. Hopefully that gives you a good start and you can work a couple of problems.